Okay, so what I personally am very interested in, all of this has been sort of prelude, is what happens after the explosion. And there's a bunch of different things that can happen after the explosion. One is just the expanding blast wave from the supernova. It continues to expand and sweep up interstellar matter. And there's a lot of interesting things that can happen, at that blast wave. All right, so SN 1006 went off in the year 1006, so it's a little over 1,000 years old. And this is an X-ray image of the supernova remnant. And we'll talk a lot more about it a little bit later. So what we're seeing there is the outer blast wave of the supernova as it expands into interstellar space. So that, there's really interesting physics that happens there. Back in at the center, where the remnant of the original star might be, you've got, in some cases, a pulsar that gets left behind. So a neutron star that's highly magnetized and spinning, and it produces pulses of emission. We'll talk more about that. Those pulsars, they don't just emit pulsed emission, they will also throw off a wind in all directions of energetic particles. And that wind can develop a nebula around the pulsar. And so what we have here is a really famous object, especially in high energy astrophysics. It's very bright in the radio, in the X-rays, and particularly in gamma rays, in the range where I study where I do most of my work. And so what you're seeing here is in blue in the center, the nebula as it looks in X-rays, and then in I guess green is optical emission in the nebula, and red is radio emission. And you can think, X-rays are much more energetic than optical light, which is much more energetic than radio light. And that difference in the energy of the radiation corresponds to the difference in the energy of the particles producing the radiation. And so you have, near the pulsar, you have processes going on that are accelerating particles to extremely high energies, creating cosmic rays. And those processes, then the cosmic rays, they diffuse out into this nebula, and they radiate and lose energy. And so they're most energetic when they're close to the pulsar, and as they wander off, they lose energy and and tend to contribute more, in optical instead of X-rays, and then as they proceed further, more in radio rather than optical. And then this last fellow on the right-hand side, this Cygnus X1, X, because it's very bright in the X-rays, it's a binary system. It has a massive star and a compact, lower mass companion that in this case, it's not so much lower mass, and it appears pretty solidly to be a black hole on the order of 10 times the mass of our sun. And that black hole is siphoning off some material from this companion star. And as that material swirls around the black hole, it gets heated up. Its gravitational energy, as it's falling in towards the black hole, gets converted into kinetic energy, and then the material becomes very hot and radiates. Yeah.
What accounts for the filamentary structure in the crab? Is that just the surrounding material?
So yeah, that's a great question. This filamentary structure